Hey everyone, and welcome to class number 2 of Raspberry Pi Pico RP2040, the deep dive. Before we dive in, just a couple of notes. So first of all, there is this document with all the links and resources from last time. I'm sharing the link. Hackaday shared the link. Thanks, Christina, in the chat, so you can follow it. And based on the feedback from last class, this time I included the agenda. So you can find the agenda in the document and see what we'll be talking about. Also, whenever we have a reference to the datasheet, there is like the section number. So this can be very useful for some of you based on your feedback. And other than that, let's see. So there is like a tense situation going right now in Israel, and there is a low chance, but there is still some chance that there will be alarm during the class, in which case I will have to go to a shelter. So just so if that happens, you won't be surprised. Again, there is a pretty low chance that it will happen, but it may happen. Cool. And before we, I share my screen and we start with, thanks, David. Before we dive in and I share my screen, if any of you is taking notes and wants to share them with the rest of the people, just let me know and I can add a link to this Pi Pico class resources. I think it can be really useful if you take notes and want to share them with other people. All right, so sharing my screen. How do I do this? Zoom, help me. There is screen share. Yeah. All right. And this is my screen share. And now you should be seeing my screen. Let me make sure that I can still see the chat. So I can see all the smart things that you're writing there. And yeah. Can you see my screen? Yes, no? While I'm waiting for your answers, let me just update you about a few changes in the emulator that we are using. So first of all, we had this program last time. It didn't really, we had some glitches with the emulator. I fixed them all, I promised. Now it should be fine. So we had that program we built last time that should alternate the LEDs. And now it does. And in case you missed it, we have this like, I added some comments and everything, but you have this in the document, code samples from the class from last class. So if you want to check it out. Now, in case I ran a poll and some of you have a RP2040, a physical one. In case you want to run those examples on your physical Raspberry Pi Pico, you can just F1 and then download UF2 binary. It's a new feature I added based on your feedback. So now you can just click on it and it will download, it will take a second or two, and it will download a file you can just drag into your Raspberry Pi Pico and run the same code from the emulator on the physical Pico. So it's super useful if you want to copy code from here or to run the program from here on the Pi Pico. And the opposite is also possible. You can F1, load a hex file and start simulation, and load any hex file. For instance, if you use the Raspberry Pi examples repo and compiled one of the examples, you can run it here just by loading the hex file and starting the simulation. So just a few notes about these new features that are pretty useful if you want to test the code on your physical Pi or import code from somewhere else like the Pi Pico SDK. So yeah, let me see what else. So last time we had this thing with GPIO registers. We have seen how we can use, let's close this, we don't need it anymore. We have seen how we can use the GPIO registers to, control the like the hardware registers to control the GPIO directly. So we have this Arduino program here. It blinks an LED. And then instead of like using digital write, instead of using the Arduino API, we can go low level and write to the registers directly. Let's just do it as a real quick recap. So we had this section about the SAO, and inside the SAO, actually, I think there is a shortcut from the GPIO. Yes. So yeah, there is this GPIO out register, and we can write, there is like GPIO out set or clear. Let's use the GPIO out clear to just turn off a GPIO. So we can do define GPIO out clear, and then it's a pointer to 32-bit integer, and it's SAO plus this offset. So this is the offset of the register plus the SAO address space, which is this. Okay, and then we want to dereference it, so we can use it as just assign a value to it. And then instead of using digital write LED low, we can do set this specific bit in this register. So we can use the bit macro of Arduino. So set bit 1, and that should keep blinking LED 1, but this time turning it off is done by writing to the hardware register. And behind the scenes, it's what digital write is doing. So there is no problem if you want to mix and match. But this code is portable. I mean, digital write is portable. This code is not portable to other platforms, so it ties you to the Pico. So cool. We have seen this last time, how to do this thing with GPIO. And now I want to show you another peripheral. This time it's the timer. So we are going to use the timer registers. So I think we briefly, last time we briefly looked at UART. So let's take a look at the timer. So the system timer peripheral, it has a microsecond time base for the system. And there is a single 64 counter incrementing once per microsecond. So it counts microseconds, 1 million per second. And you can read and write from it. And there are 4 lumps, which we will see in a moment. So the first thing we are going to do, we are just going to take a look. I mean, we could keep reading on the counter, how it's split into 2 registers because it's 64 bits. But basically, these are the registers, time LR to read the high part and the low part of the time. And let's go to this register and try re-implementing delay. Now, so first we re-implemented digital write. Now we are going to replace delay with our own implementation. So we are going to take this timer LR. Let's define this register, time LR. Time LR is at this offset, and it's basically an offset from this timer base. So this is the timer base. I just copy pasted it from here, the base address of the timer peripheral. And instead of like repeating this thing for every register that we want to define, we can just define a macro for that. So let's call it mem32, and it will accept an address and just, provide an easy access to the contents of the memory contents of this address. I'm also going to add a volatile keyword. I'm not sure if it's required, but if we don't put it and we read from a register and then immediately we write to a register and then immediately read from it, the compiler may optimize that out. So volatile makes sure that won't happen, that every time that we are writing to a mem32 register, then the compiler will actually write. It won't optimize that. And then we can just say, instead of this, this is mem32. Let's just quickly, and this is also mem32. Let's just quickly check that this is still working and the LED still blinks. Yeah, still working with this new macro. Cool. So now let's use this timer LR to define our own variant of delay. So let's call it timer delay. And what we are going to do, actually, yeah, okay. So actually what we are going to do, we are going to take the number of micros. How many microseconds we are going to delay. Microseconds, yeah, just not to clash with the Arduino functions. Seconds, thanks. And then we are going to have target time, which is just time LR plus microseconds. And then we can do while time LR is less than target, basically do nothing. That's a busy wait. So we are just waiting for the time to pass. And now we can replace those delays with time delay. We need to add 3 zeros because now it's microseconds and not milliseconds. And if everything works well, the LED should still blink LED number 1 roughly once, or actually once a second. So now we re-implemented delay using this timer peripheral in just 2 lines of code. But actually, the timer has a mechanism that can help us instead of counting or waiting for the time to pass and implementing this mechanism ourselves. It has this thing called alarms. We are going to learn how to use them, and then I'm going to show you why they are super useful. So in order to use the alarms, there is like this section about the alarms, and you can see that it has 4 alarms, and it outputs a separate interrupt for each alarm. We'll take a look at that in a few minutes. And the alarms match on the lower 32 bits of the 64-bit counter. So it's basically the microcontroller basically compares the alarm value with the value of this register, which is exactly what we are doing here, but it's done in hardware. And it can count up to 72 minutes ahead, which is more than enough for our purposes. So in order to enable an alarm, we just need to write the time for the alarm in the specific alarm register. So there are like 4 alarm registers for each of the alarms, and as soon as we write to them, it arms the alarm. So let's try that. We are going to use alarm number 1, for instance. So we know that alarm number 1 is at offset 14. Let's define the register. So alarm 1. Actually, we can have another helper macro timer edge offset that will just do mem32 and this plus offset. So we don't have to repeat the timer base for every single timer. So we can do this and then just remove this. All right. And then so as soon as we write the target time into this alarm 1 like this, the alarm will be armed. That's what the datasheet says, and the alarm will disarm itself once it fires and can be disarmed early using the armed status register. So if we take a look at this register, the armed register, it indicates whether the alarm is currently armed, or for each alarm, it indicates whether it's armed or not. Write to the corresponding alarm X register, which we just did, arms it. And we can, writing 1 to this register will disable the alarm. It says WC, which means write clear. Whenever we write a value, it will clear that bit. So as soon as we do this, we can assume, or the datasheet tells us that this armed register, the corresponding bit, which is bit number 1 for alarm number 1, will be set to 1, and it will disarm the alarm as soon as the time passes. So we can basically change this condition to let's keep it going. Let's keep waiting until this bit is cleared, like the bit read. Sorry, bit read reads the bit number 1 of this register, while this bit number 1 while it's set. We want to wait while it's set, and as soon as it clears, the while will stop and a timer delay will end. So let's run this, and it compiles, and you can see it blinks just as usual. And just so it's more interesting, let's change the delay to 250 so it works a bit faster. And you can see I'm actually doing something. It's not the same. I mean, we get the same result. That's the third approach already. So that's how we use the alarms. We just set the target time and then wait until this bit goes to 0. And the reason I used alarm number 1 and not 0 is that the Arduino core for the Raspberry Pi, the one that we are using to run our code, is actually using alarm number 0. And we can see this. One way to see this would be to print the value of armed when the, let's print it in binary. When the program begins, you can see that the value of this, serial 1. I said I would make this mistake, and now I did. So yeah, so you can see that it's 1. So basically, the operating system or the Arduino core already uses that's bit 0, so it already uses alarm number 0. And if we do this print here, we'll see that both alarms are armed, both 0 and 1. So that's how we use the alarm. And it's pretty nice. We implemented our own delay in just 2 lines of code. Let me just copy this to the document so you can have this later if you want, this piece of code. And what I want to do next is actually show you how we can do it sort of asynchronously. So instead of like blocking the main loop while we are waiting for this timer, we can also use interrupts. And interrupts are a way for the hardware to tell us that some task has been completed or some condition has happened, like a GPIO has changed. So basically, it's a way for the hardware to notify us about external or internal events. Let's start learning about interrupts. The first thing we're going to do, the information is a bit scattered, and we are going to go over a few different documents. So try to bear with me. And if you have any questions, just ask in the chat. The first thing we are going to look at is inside the system description, there is this interrupt section, 232. And again, that's in the agenda. You can find it here. So there is this interrupt section, and it has this list of interrupts. It says that each core has like 32 interrupt inputs, even though only the lower 26 are actually used by the hardware. And then we can see for each interrupt number, the hardware that is connected to that interrupt. So we can see that the first 4 interrupts are used by the timer, specifically for the 4 alarms that we have. And that's what we are going to use in a moment. And then we can see there is an interrupt for the PWM, for the USB, for the PIO, DMA, for the UART. So basically for all the peripherals, more or less. And it says that the implementation of the interrupts is done by the NVIC, ARM Nested Vector Interrupt Controller. And this is a piece of hardware that manages the interrupts. And if we check out section, I think that's 243. Yeah, there is like 245 actually. There are a few words about the NVIC, really few words. It says that they are connected, external interrupt signals connect to the NVIC, and the NVIC prioritizes them, and software can define the priority, blah, 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 blah. And we can see that there are like a few registers. Like there is this interrupt set enable register, which we can use to tell the hardware which interrupts we are interested in. So you can see that we can use it to enable interrupt and also to determine which interrupts are currently enabled. So this sounds useful, and we are going to, anybody has a question or something like that? I hear somebody coughing. Okay, no, perfect. So if you are not muted, please mute your mics. Somebody asked if this belongs to ARM. So NVIC belongs to ARM, not the specific IC. That's a great question, because that's the next thing I'm going to talk about. But before that, let's take a look at the value of this NVIC. So this is the offset of the NVIC. How do we call this register? That's ISCR, interrupt set enable. So define NVIC ISCR, and this is the offset. And you can already see that this offset is relative to M0 plus. M0 plus is the ARM internal registers. These are the registers that are internal to this ARM Cortex-M0 core. So these are a part of the ARM architecture, and they are not specific to the Pi 0. And this is the base, the offset. Let's just plus them. So the base address plus this offset. And we can just print the value of this register. Let's print it in binary. And as you will be able to see in a moment, you can see that there are only a few interrupts that are enabled, like number 0, 1, 2, 3, 4, 5, number 5, and I don't want to count. So if you want, you can try it later and see which interrupt is that. But you can see that number 0 and number 5 are enabled. And if we check the interrupt table, we can see that number 0 is indeed the timer IQ 0 for the alarm number 0. And number 5 is the USB, because the Arduino core uses USB for the default serial console. So it probably enables the USB interrupts to receive events from the USB hardware. And back to the question from HLLC8. So is this something that is specific to the Pi Pico, or is it ARM? So this interrupt table is specific to the RP2040. However, the NVIC isn't specific, and that's the reason there is no information about it. There is like only the list of registers, but there it says you need to check out the ARM M6 architecture reference manual for more information about those registers. And that's what we're going to do. So we are going to check the architecture reference manual, also called ARM. So that's the ARM ARM. And what I'm going to show you is how instructions work. So how do we define the handlers for an instruction? We know we now learned we can use this register to enable and disable interrupts, but how do we tell the microcontroller where is the function, or which function handles each interrupt? So for that, we need to understand that interrupts, this is, by the way, the ARM, the ARM ARM, and I will just put a link in this document so you also have it, the ARM ARM. And as soon as you open it, the most important or the most useful thing you can do, you can just download this to your computer. I think it's much more convenient in form of a PDF file. And then once you have it as a PDF file, you can just open it like that and go to section, I think that's in B1.5, yeah, exception model. And you can see this as like, so interrupts in ARM are just a specific case of exceptions. And there are a few exceptions that are like built in, like this reset, where this is the where the code starts executing from. And all those exceptions like hard fault, whenever you have your access invalid memory address or something like that. Cystic, which is another timer built into ARM. But the interesting thing for us is that the interrupt starts at number 16. So interrupt 0 is exception number 16. And that's a bit tricky. We need to remember that. And there is another section here that shows us how the vector table is organized. So this just shows the exception numbers, but if we want to know or to set the handler for a specific interrupt, then we need to go to the vector table. And the vector table is just a table of 32-bit values. And then the exception number, if you go to the like entry number 1, that would be the handler for exception number 1. And offset 0 is reserved for the initial value of the stack pointer, not very interesting right now. And where can we find this vector table? Where can we see this list of exceptions? So there is a register called VTOR that points to this exception table. Sometimes it's fixed in some of the microprocessors. In the RP2040, it's not fixed. It's something that the user can set where this exception table resides, a vector table resides, and we can do it by setting the VTOR table. So let's go back. We don't need this anymore. We have the PDF. We are going back and forth between the datasheets. So let's go back to this datasheet, and in the list of registers of the Cortex-M0 in the Pico RP2040 datasheet, if we scroll down a bit, you can see all the NVIC registers, and here is this VTOR register, vector table offset register. So it holds the offset of the vector table. So let's copy it and have it as well. So that's the VTOR. And let's see, where is this table stored in our code? So we can just print this value as hexadecimal. And we can see that it's actually stored. Let's remove this. We don't need it anymore. We can see that it's stored at 20 million. And if you remember from the previous class, this is actually the start of the SRAM. So let's go real quick to this address map, and you can see it's just at the beginning of the SRAM. So whenever this Arduino core starts, it just loads there the vector table and then set VTOR to point there. And the next thing we are going to do, we are going to dump this table so we can see which interrupts handlers are currently configured. So let's define the method that will do that, dump vector table, and it takes nothing. And basically what it does is just goes from 0 to 16 plus. So we said that the interrupts actually start at number 16, and then they go 16 plus number of interrupts that we had. And the Raspberry Pi datasheet says that we have 26, so we can go until 16 for the exceptions plus 26 for the interrupts, actually from number 1, because number 0 is not an exception, it's the SP pointer. And then we can just print this value. So we could use the Arduino API like the println, but in this case, it's actually more convenient in my case to use printf, and it works here in this Arduino core, just redirected to the serial output, so a bit more convenient. And then we can just read mem32 at VTOR plus I times 4, because we need to go 32 bits down for each exception. Yeah, and then we can just vector table, and hopefully in a moment we'll have like an error missing. Oh yeah, I need to add I++. So somebody is asking if Arduino boot is doing all of this. Who? Something messed up. Oh yeah, I need to add I here to the printf. So I'm not sure if it's the Arduino uses EmbedOS, the Arduino core. So I think it's EmbedOS doing this, or maybe it's even the bootloader, that the boot stage 2 that does this. We can check it later. But that's a good question. Anyway, we can see this dump of addresses. And in order to make it a bit more readable, I prepared a list of all the interrupts so we can, and the exceptions. So instead of having those numbers, we can just use this map that I prepared and print their names. So we can just the list of exception names from the ARM, those exception names followed by those interrupt names in a nice array. And then we can just, print vector names. Yeah, it just, let's say, wanted 20s, and we want to align them so they are nicely printed. And when we run it, we can see now all the interrupt handlers. Let's just copy it for a moment so we can see everything at once. And yeah. So this is the table, and you can see that most of them have this value 1C1, or these are actually not valid. These are like unimplemented, so we can ignore them. These are the actual exceptions, but we are interested just in interrupts, and we can see that most of those interrupts has this value, which is probably the missing interrupt handler. These are the interrupts that are not enabled. And then for the interrupts that are enabled, we can see this like the address of the timer IRQ0 handler. So this is the function that handles this interrupt. And same for the USB. And we can see that the other interrupt that we have seen before, the other one that was enabled, is probably this UART0. It makes sense because we are using the UART. And then all of those are like unused right now by the code. And somebody is asking if this address space is in the flash, the XAP. Yes, this is like the flash where our code resides and also the Arduino core resides. So it makes sense that those handlers will be in the flash, even though I think you can, I know you can place code in RAM. I think you can even place interrupt handlers. I haven't tried. I don't see any reason why it won't work though. Cool. So we have this piece of code that dumps the vector table, and just so you have it, let's save a copy and give it a name. So yeah, I will tidy it up later, but for now, let's just call it Pico dump vectors. Now. And save this and then lock it so I won't make any changes and save them by mistake. And yeah, let's add it to the list here. And yeah, dump vector table example. Yeah, so somebody is asking about timer IRQ0, why it's enabled by this core. I'm not sure why it's using it for. If you want to, we can look into that in the Q&A session. That's a good question, and I would love to explore that. But for now, let's see how we can harness interrupts for ourselves. So we are going to remove this code for now, this dump vector table, and go back to the mission of blinking this LED. This time we are still going to use alarms, but with interrupts. So the first thing we want to do is to enable, to create this interrupt handler. So let's create void alarm1 IRQ handler, or let's call it just alarm1 IRQ. And this will be our interrupt handler. And inside our interrupt handler, we are just going to toggle this LED. So let's define this. This is like we defined a register that would just, clear the pin, but we want to toggle it. So let's take a quick look at the data sheet. Where is this XOR? It's in offset 1C. So 1C. So whenever there is like an alarm1 IRQ, we want to just, toggle this pin GP1. And then the next thing we want to do is arm the alarm. So let's remove this timer delay. We are going to replace it with the interrupt, and then say just like, let's say we want to blink every 250 milliseconds, this number of microseconds. So we want to set the next time the alarm once. And now the next thing we need to do is just, to set this vector table entry. So we can do something like mem32 VTOR plus, we need 16 to skip past the exception, all the exceptions, plus 1 because that's IRQ1. We can see here it's where was that? The interrupts. Yeah, timer IRQ1 is for alarm number 1. Yeah, we can define a constant for that to make the code at least a bit more readable. So plus timer IRQ1 times 4, because each entry is 4 bytes, 1 word, and this horrible thing equals to alarm 1 IRQ. And at this point, it will probably complain because I'm trying to, this is like uint32, and then this is not uint32. And I will probably have to typecast it. Let's see. Yeah, I'm assigning a, oh, we can remove this. Unterminated comment. My God. Okay, so it will probably complain now because yeah, it's alarm 1 IRQ because it's not an integer, so I will cast it into an integer. Yeah, and we don't have this anymore. We can remove the loop for now. And yeah, we need to convert it. So let's just typecast it. And yeah, so at this point, the code runs and the LED doesn't blink yet because we have defined this handler, but we are still missing a few things. And let's write them down so we know what we need to do. So step 1 is define the handler. Step 2 is enable the interrupt, the NVIC interrupt inside this NVIC ISCR. So that's exception interrupt handler. So that's from the microcontroller side of things. But we also need to do some stuff for the timer itself. And let's take a look at the timer to see what other stuff we need to do to make this interrupt mechanism work. So let's take a look at the timer. I think it's section, yeah, in the alarm. So if we want to enable an alarm and have an interrupt, we also need to enable the interrupt inside the timer peripheral. So you see, you need to first enable the interrupt at the timer in this register, then enable the appropriate interrupt at the processor, which is this NVIC register, and then write the time I would like to the interrupt to fire to the alarm register. And then it's at the armed bit. And after the alarm is fired, the armed bit will be set to 0, but I also need to clear the interrupt by writing this 1 to the bit in int r. So let's write it down. The first thing we need to do is actually, before we do that, I mean, we can define the exception interrupt at the beginning, but then we need to enable the interrupt in the timer int e register, and then and I'm seeing you have a couple of questions in the chat. Let's leave them for the Q&A session. Please take note of them, and we will get back to them in the Q&A session. So we need to do this, and then we already have this, and then yeah, and then number 4 is set the alarm 1 register to the target time. And finally, here it also said once the interrupt is fired, we also need to clear this the latched interrupt by writing 1 to the bit in the int r register. So int r clear the interrupt in int r. All right, let's do this. So defining the exception handler, we just did it. Cool. Now we need to enable the interrupt in this timer int e register. So let's see where this int e live. This int e is at offset 38, and you can see there is 1 bit to each of the alarm. In this case, we want to enable alarm number 1, so we will set bit number 1. Let's define this. So we have this int e at this offset, and then we can say int e, we need to set to enable bit alarm 1 RQ. And we can also, since this is a peripheral, we can also do this by writing to the, if you remember from last time, we talked about this atomic memory access somewhere here. Yeah, atomic register access. There is like a shortcut we can write to this, add this value to the memory address, sorry, this one, to enable this bit, but it doesn't really matter. This will also do the trick for now, just using this C syntax. And then we need to enable this interrupt in this register. So yeah, enable it. So just write 1 to that bit as well. And oh, sorry, this, we don't need to read the value. This register is actually, you can see here, whatever we write there, writing 1 will enable the interrupt, and 0 has no effect. So it's only setting interrupt. So we don't need to or equals it. And we want interrupt number 1 timer IRQ. And finally, we need to set the alarm to the target time. So this is the target time, current time plus this constant. And yeah, let's set the pin to output just before we do all of that. And finally, inside this IRQ handler, we also want to clear the interrupt in int-er. So let's see. Inter, that was timer registers. Where is this int-r? Row interrupts at 34. And this is a write clear register. So whenever we write a value to it, it will just clear that bit. Very nice. So we don't have to use those atomic register access. We can just write a value directly. Okay, so let's define it. So int r, I think that was 34 hexa. And then I can say just int r equals bit alarm. Oh, sorry, it should be 1 and bit 1. Just, you know, we want to clear alarm 1, so that bit's number 1. And coincidentally, it's also equal to the RRQ number, but it's not true in all the peripherals. It just happens to be so in the timer. So we clear the interrupt in int r. And now let's hold fingers and see if this works. Let's try to run it and see if the LED blinks. And if not, we'll have to trouble. Oh, it blinks. Perfect. So yeah, so that's how you do it with interrupts. And now the cool thing about it is that you can now do whatever you want in the loop. It's like running sort of concurrently as another background thing. So for instance, we can do something like for int I is 1, I less, or from 2, we are going to just play with the other LEDs, I less than 8 and I plus plus, and then we can say pin mode I output. And then here we can just do something like digital, or, you know, just have this, use this. Yeah, let's use digital write just to make things a bit more spicy. Just, you know, that's the Arduino way to toggle a GPIO pin, delay 50. And finally, I want to remove this LED. And let's make this one green, the first one now. Let's make it green. So it's a spatial one, the one that we are going to blink. And let's run this. And if all works well, yeah, you can see this is blinking and those LEDs are doing their things in the loop, and everybody is happy. That's how interrupts are useful. So before we go on, let's just save this as a copy and call this Pico timer interrupt, and share the link with you so you have it as well. Cool. So that's the we said that's the Pico timer interrupt. Cool. One more word about interrupts before we move on. Instead of doing something in the loop, we can also do something like, and this is sort of a bridge to the next. Let's just look it so I don't accidentally save on it. This is a bridge to the next section. I can call a processor function called an instruction called WFI, and it won't do anything different in the simulation. And if you run it on the real chip, you won't want to observe the difference between this and just an empty loop. But behind the scenes, it saves power. So I ran this code before with WFI and without this WFI, wait for interrupts. And using WFI saved around 3 milliamps of current. So it reduced the current consumption, the average current consumption, by 3 milliamps. And if you want, I can show you this later, the setup I used to measure this later in the Q&A session. Okay, so one quick question from the chat before we move to the next section is whether all the alarms trigger the same interrupt. So no, there is one interrupt per alarm. If we check out this, there is like RQ0 is for alarm 0, alarm 1, alarm 2, and alarm 3. This is not true for the other peripherals, like for the GPIO, for instance. This is like the SAO IRQ. There is one interrupt handler for all the GPIOs per processor, and then you have to look into the GPIO registers to figure out which GPIO triggered this interrupt. So it's the same for most of the peripherals. You have one generic interrupt for the peripheral, and then you have to look inside the registers of the specific peripheral to see, to check the bits there to see which condition or which event has caused the interrupt in that peripheral. That's basically the essence of how interrupts work on the ARM Cortex-M0. And that's a good time to move to the CPU registers and talking a bit about what is this ARM Cortex thing. So ARM has a pretty confusing, I at least found it confusing when I started. Naming convention, there are like a lot of different, or there are some different ways to categorize the microcontrollers and the CPUs. And I think this Stack Overflow summarizes this question, this topic. There are like, except Cortex-M and Cortex-A, and Cortex-M is for microprocessors and A is for more powerful applications like your Raspberry Pi, the physical Big Pi, Pi 4 or 3, or your smartphone. And you can read about the differences later. I will just post this answer link here so you can check it out later. And the other question that is interesting, and we'll get to that in a moment. Actually, we'll get to that in a moment. So another useful resource, if you want to just get a good orientation of all the like types of processors that we have, is this. Let me find. I have a link here somewhere. Yeah. The thing is, I will paste the link directly because as soon as you paste it, it just tries to download the file, Cortex-M for beginners. And yeah, I don't have it open. I will open it now. So Cortex-M for beginners. And it also gives you a quick summary of like the three different Cortex families. We are here, Cortex-M0 Plus, that's the RP2040, and it summarizes all the differences. And also one thing we are going to start talking about is the assembly language. And you can see this is like the assembly language for this ARMv6. That's the architecture of the M0 Plus of the RP2040. You see it has a low number of instructions compared with ARMv7, and there is even more in ARMv8. So other than these two cool tables, there is a lot of cool information if you want to understand like all those different processors in these families, all those processors. So I suggest to take a look at it later. Cool. And all right, so now let's talk about instructions. But before we get to assembly and instructions, there is one more thing we need to know, and that's the registers. And we are going to go back to the ARM section somewhere. I think it's in the system level programmers model registers. Yeah. I think we have it on the list. So you can see registers are like variables, local variables that the assembly code uses. And they are like only a few registers, processor registers in the Cortex-M0. They are like general purpose registers R0 to R12, which we will talk about today. And there are a few more registers that are or like R13, 14, and 15, they have like spatial roles, and we'll talk about them in the next class. And a few more registers that have status and control the CPU, and we'll probably mention them in the future. But for now, we need to know that we have like those R0 to R12, and they are just like local variables. And one cool shortcut that you can use in the simulator. So let's just, did I not save this? I don't know. I'll check it later. Worst case, let's just open a new one so I can check this later. Anyway, so, oh yeah, I can now see that I did save it. So yeah, I can just remove the stuff here and remove all of this and get a clean program. And I'm going to show you something. So usually you need to use a debugger if you wanted to see the registers. And we are going to do that in future classes. But for now, I'm going to teach you a quick way to do that in the simulator. So you can write ASM BKPT42. I will also copy this here. And this spatial instruction is usually used to set breakpoints in the debugger. But here in the simulator, it just tells the simulator to print all the registers. So that's a cool way to just experiment and see the values of registers. So you can see here, we have, I hope this is big enough, the font. We have R0 through R12, then all those extra registers that the datasheet mentioned. And the first instruction we are going to look at is called move. And move just copies value into registers. So let's say we want to, so we have R0. We can see that at this point in the program, it was 0. Let's say we want to set it to hexa 22. We just write move R0 22, and this is the equivalent of setting R0 to 22 hexa. And if we run this code, let's just clear the output, and we can see it set the register to 22. And then this ARM has a complete list of the instruction I think there is even, yeah, 2433. So if we check 2433, where is that? 2433 programs module. Yeah, we have like the complete list of instructions. So we have move that we have seen. We can also copy values between registers. So let's say we can copy this. Now this new value, we can also copy it from R0 to R1. So R1 equals R0. And let's run it. And you can see that now both have this value. And then there is like this add that adds a value to a register. So we can, for instance, let's say we want to add to R0, we can add, so this is R0 plus equals 11 hexa. So we can add values, and then we can see that the result now it's 33 hexa, or let's make it a bit larger. Yep. So this is the result. Or we can subtract. So we can subtract, like, let's say we are going to subtract 10 hexa. So that's, yeah, clear the output. Yeah, and you can see this is actually minus equals 10. And you can see the result. You can do fancy things like multiplying. Like, let's say we have 2 and 6 in R1, and then we can say multiply R1 by R0. So actually 2 by 3, that would be easier to see in hexadecimal. So we can say this is R1 0 2, R1 equals 3, and then R1 equals multiply equals R0. And yeah, you can see R1 is now 6, which is 2 times 3. So this is how you can experiment with assembly in your code in the emulator. I will show you one more cool shortcut. Instead of repeating ASM multiple times, we can use this C++ way of writing multi-line strings, just R quotes open parentheses, and then we can just write the instructions directly. Like let's say PKPT42. Let's remove all of those. And yeah, and now we don't need this semicolon. Yeah, and now you can see, let's run it again. And now you can see like it still runs those 2 instructions and sets the breakpoint. So just like we have seen, there is add, there is sub, there is mul, there is null, there is mul, there is also move. So copy registers or copy value into registers, arithmetic operations, and then there are like bitwise operations, like there is AND, bitwise OR, bitwise XOR. So bitwise operations, let's, for instance, we can move R1 20, and then we can just, R1 is 20 hexa. And then we can bitwise OR R1 with R0. So no need for semicolon here. So basically R1, just R0. And this should equal 22 hexa, because we are, yeah, you can see the result here in R1, 22 hexa. So yeah, as you can see, it's just like you have those registers, which are very similar to variables. And then you can put values there, you can perform operations on them, and all those bitwise operations. And just with those instructions, we pretty much covered, you see, all those move and logical. We covered about 1/3 of the instruction set. There aren't so many instructions. You can see the table spans around 3 pages, and we already covered like move, add, subtract, multiply, and the logical, or at least some of the logical. We still haven't done those, but we'll get to them. Anyways, so this is somebody pointed in the chat. This is called RISC, reduced instruction set. There aren't so many instructions. If we check the architecture reference manual, there are like, there is like, I think it's A6. Yeah, there is like this list of instructions, and you can see it goes, it has like 77 instructions in total, like each instruction is a section, but many of them are like repeating, like there are like 3 entries for add, and same goes for like subtract. And we are going to cover some more instructions in the next session, like loading and saving data into the memory, because how could you, how in the world could you build programs with just 12 or 13, R0 to R12, with just 13 variables? So if you want to interact with the memory and the peripherals, that's how you need, that's where you need to read and write values from the memory, and there is a separate set of load and store instructions for that. So that's what we are going to do in the next class. But for now, I invite you, to just hop on the simulator and just, play with those. I'll copy it into the chat with those instructions, not the chat, into the document with, and also this example, just so you have a boilerplate you can use. So you can play with, and I can't spell arithmetic apparently, so you can play with all those instructions until the next session, and just get a bit more comfortable with writing assembly code. So, well, that's been a long ride. Thank you for. I hope it hasn't been too intense, and thank you for joining this class today. I'm now going to take questions in the Q&A. And just before that, I want to say that we are working on defining the final project for the course. I have a few ideas. I'm still trying to decide how exactly that would be like. So I hope to announce more details in the next week. So just so you know that if you want to receive a certificate at the end of the course, there will be this project. You will have to do it. It will be a project that will require some work. I estimate around 10 or 15 hours of work in total, maybe less, maybe more, but more details coming next week. Cool, so we have 5 more minutes. Let me quickly try to show you how I did this thing with the WFI. So we have this code, and now if I'm using it with just an empty loop, then I mean, it doesn't do anything. There is no observable difference between this and WFI. But now let me share my desktop, my physical desktop, not my virtual desktop. Let's see if I can get the camera setting right. So trying to share my desktop. I hope that won't be too embarrassing. So yeah, so on my desktop, if it ever loads, okay, I don't want that camera. I connected another one. Oh, I forgot to connect the other camera. It's my bad. And then Zoom is using the main camera. Okay, so issue fixed. And now you can see I have this setup here. So this is the Nordic PPK Power Profiler Kit. It allows me to blind the camera and also measure power. And then this is connected to the Pico that is also, sorry about missing focus, but the Pico is connected to the Raspberry Pi, so I can program it or debug it, which is not really important right now. So the first thing I'm going to do, I'm just going to use this variant without WFI. I'm going to download the UF file so I can upload it to my Pico, download UF2 binary. And at the same time, I'm going to plug my Pico into, let's show this in folder. So yeah, I've done this before. So let's just remove all those. and let's call it firmware no WFI. And the next thing I'm going to do, I'm going to plug my Pico into the computer so we can upload this code into it. So plugging it, and let's drag this file. So uploading this firmware, and you should be able to see the LED, or maybe not, blinking on the Pico. Did I miss something? Let's try that one more time. Oh, yeah. Wait a second. Let's try that one more time. Yeah. Oh, yeah, of course. I'm blinking the wrong LED. I need to blink LED number 25. That's the right one. Not LED number 1. Let's just run it in the emulator once to see that it blinks LED number 25. Yeah, now it blinks the correct LED. Oh, no. In ask whether you have to do this, use these plugs. No, I just use this clip, so I don't have to solder anything into my Pico. And I'm using the SWD to load and debug. That's true, even though now I'm loading, let's download the UF2 again. Now the one with the right pin, with the correct pin. Firmware, no WFI. And then copy it into the Pico. So now I'm just using the USB, but you can also use this serial debugging protocol to load the firmware. So copying this. Oh, and now it's blinking. Great. Yeah, I'm loading through USB. You can see it's blinking. And now I'm going to unplug it from the computer and plug it to the into the PPK. So let's see, it's plugged into the PPK. You can see here the 2 wires going from the PPK to the Pico, and going to open NRF Connect, which is the Nordic Semiconductor app. And as soon as it launches, Power Profiler, and now we can see, let's select the device, PPK2. Let's put it side by side with the camera. Side by side with the camera. And now the LED is not blinking because the device is not powered, but I'm going to switch the start the recording. And now I'm starting the power from the PPK, and nothing happens because one of the wires is disconnected. Brilliant. Okay, now you can see the LED is blinking, but this time it's powered from the PPK. You can see this peak when I connected the wire, and this is the power consumption. And you can see like this is like the on and off period of the LED. And if I zoom in, you can see that this is the off period. You can see that I need 30 milliamps on average. And if now, so that was about 30 milliamps. And now if I just change the code and add this WFI and download the UF2, and let's just upload this again to the Pico data code. That's showing folder, firmware, that's with WFI. So that was 30 milliamps. Yeah, 30 milliamps low cycle when the LED is off without WFI. Now with WFI, let me go back to this and just plug it back to the PPK now that I disconnected it from the USB. And just restart this recording. And now you can already see the numbers are a bit lower. For some reason, the LED stopped blinking. That's interesting. Not sure why is that, but you can see like the power consumption is, let's try to restart this for a moment. Maybe that will help. Yeah, now it's blinking again. And let's start the recording. So now you can see this is now the power consumption when the LED is on and off. And if we zoom in, when the LED is off, the average is 5 milliamperes. So just by adding WFI, we just shoved about 5 milliamperes of current. So 25 low cycle with WFI. So now you have seen in your eyes the impact of just adding this WFI instruction and shutting the core off while waiting for this alarm. And there are like, you can use the RTC to even achieve single digit milliampere current consumption, but we won't get into that. All right, so that has been like a nice extra bonus just for those who stayed until the end. And I hope that you enjoyed today's session. I see that my camera has reset. Now you can see the whole room. Hooray. So have a great week, and I hope to see you again next week. And if you have any questions, hit me on Discord, or I also try to check the Hackaday chat regularly, or on Twitter. You have my Twitter here. And that's it. See you next time. Goodbye.